Hey guys, here's the first, maybe last, I'm not sure how many installments of videos about how to use the Autodock software suite. I will maybe refer you to maybe other web tutorial or something like that for actually installing Autodock. But you'll need to install Autodock 4. Okay, of course this would be the best version, or one of these. And then in addition, you'll need Autodock tools. Okay, and that's gonna be right here, and of course it'd be ideal if you are installing these, but these are kind of okay. And then yeah, you might want to also install Pymol. It's great software to look at stuff with, but with that assumption you've already installed Autodock and Autodock tools. And the other thing you should do is go and find like where the Autodock was installed and where it's installed. Find these two executable files, Autodock 4 and Autogrid 4, and then copy and paste that into a folder in which you're going to place all the relevant files in. You need one of the quirks of Autodock is that you need to kind of have everything you need, including the executable files for Autodock 4 program and an Autogrid 4 program, all in the same folder, along with the PDB protein files and the ligand files. So if you need to help to figure that out, let me know. The location of those things are going to be different depending on whether you're using Windows, Mac, or Linux, and then even within those, sometimes you can have different options. So I'll let you figure that out, or get some help from me, or look at like a YouTube tutorial about that bit. But first, you need a protein data file. And of course that's another kind of thing that's going to require some help perhaps, and then of course on the day that I'm making the videos, it seems like that website is having some trouble. Well, now it opened, but you can search for some protein, whatever protein that you decided you want to study. In my case, I'm looking at a cytochrome P450 enzyme now, protein. I actually, the PDB file that I'm using actually did not come from this website, because this crystal structure of the protein that I'm actually using in this example, there's no crystal or NMR structure data available for it. I used an AlphaFold to fold a particular sequence of amino acid. Only the sequence information is available, and I had the AlphaFold algorithm. It's kind of an AI algorithm, fold that sequence based on the homology to the known structures. But if you want to know how to do that, that's kind of its own thing. I'd be happy to show you how to do it, but that's another like adventure of its own. So for a beginner, it might be easier if you just find crystal structure. Some structure that is known. In other words, like something you can find on this PDB protein databank website. And let's say you want this particular protein, then all that really you need to do at this point is to download the PDB file. Okay, and that PDB file needs to be placed in the same folder, like we said, with the Autodock 4, Autogrid 4 that you copied from where they were installed into a new folder, and then save that PDB file This is a PDB file that I made. Okay, and then as far as the ligand goes, one way to search for that, you could go to PubChem website and search for a particular compound if it's known, obviously, and then you can look at this 3D structure of that particular compound, and you can download the SDF file. Or you could actually display the SDF file. It's actually a text file that looks like this, that is a coordinate of things, and then you can go to cheminfo.org, but it's good to just search for OpenBabel online, and you can get to this website, and then you can copy and paste that here as the input. Now sometimes if the original 3D file looks weird, like as in that was the original structure where everything kind of looks flat here, and so the OpenBabel or the SDF file looks weird, then the resulting file might not be really workable, and then in that case you might have to draw the structure in ChemDraw like this, and then save it as SDF file v3000 or whatever, and then you can drag and drop that SDF file into here, right? And then you see the input is right there, and then you can you need to specify what kind of input you're having. So the input is an SDF file. The output of the ligand molecule that you want is PDB-QT format, and then hit convert. And once you do, it's converted into the PDB-QT format, and then you'll need to download this. And once you download, you'll want to rename it so that you know what it is, and then again place that file into the same. So here's the renamed PDB-QT from OpenBabel website that I saved into the same folder. Okay, so now once you do that, you'll want to open Autodock tools, and again the way that you would do that would look different depending on what operating system you have. If you have the right good operating system, you could call that program from a command line with the command ADT, which stands for Autodock tools. Might take a minute for it to open. And if you've opened this program many times over, it'll kind of hang here a little bit because they really want you to register to make it, a little annoying. But I'm just gonna do the registration later at some point. So here's Autodock tools. One of the first things you should do, and this is kind of a quirky thing, but go to Preference, Set, and under Startup Directory, you'll want to get the directory path to the directory that you want to work in. In my case, it's in a home directory, my username, Dropbox, Autodock, MMBMP, and then type in that startup directory path, or in some OS you could click here and copy and paste the path directly from the file manager. And then you can copy and paste it into here, and then click on Set, Make Default, close it. And what that allows is every time you click on Open, it'll default to that folder. Now that seems trivial, but this is a good step to take. Sometimes the bugs in Autodock tools make it crash if you skip this step. So now we're in the working directory. I'm going to open the PDB file that I had created, and it often should look like this. Now, some of you may need to do the this step where you look for you repair missing atoms, and that's because well, actually, let me take a step back. If it's a crystal structure, you want to do this command, delete water molecules. And you might notice like red or whatever dots that were all over the place disappear. Those are the placement of water molecules that were included in the X-ray crystal structure, and it'll mess things up, so you want to delete those. And sometimes the X-ray crystal structure is not perfect, and there's actually missing atoms that should be there, and then if there is, it might give you an error, so you might want to repair missing atoms, which might take time if you don't have a strong enough computer. And most of the time your structure will not even contain the polar protons that actually make a difference. So go to, after you add missing atoms, in my case I know that there's no missing atoms, you want to add hydrogen. Most of the time you could just add the polar protons only, like I did. And once you add the polar protons that might have been missing, you'll want to add Coleman charges. Those are the sort of theoretical electrostatic charges that polar functional groups should have that might be missing from the structure. And then oftentimes you want to go back to charges and click on check total residue, and you'll want to click the button that's above the dismiss button if it pops up. That will distribute the charges evenly among the whole protein molecule, and you'll want to press that button a couple times to make sure everything is distributed, and then you can click on dismiss. In my case, I didn't have to do that, but here's your protein that's sort of prepared. That's kind of the terminology. You often have to prepare your protein for the docking. If you want to look around and see what these functions are, this is the select button. Now I just selected this molecule. Within this protein, there's actually technically two molecules in it because there's a preloaded heme. So I can select that, or I can display that with a different model Q. Okay. Or for the protein, I could just show that as a secondary structure like this, and instead of showing each in single atom. So that's one way to show it if I want to. But with this, right, like I can see out of a lot of the important residues, like I don't know if you can see this very well or not, but this is where the iron is of the heme of cytochrome P450, and that's a cysteine sulfur that's directly bonded to that iron, and so forth. Okay, and so maybe I'll just keep both structure here perhaps, but anyway, so that's the prepared protein, praise the Lord. And what I'm gonna do is introduce the ligand file. So go to ligand, input, open. Here's the ligand file. Now if it loads correctly, you should I shouldn't have clicked off that one window, but you should see a window that's saying like we detect so many rotatable bonds and so on and so forth, that message. And then here's the ligand molecule I just loaded. Now that placement is just random. It's just some random coordinate in this 3D Cartesian coordinate. If you want to, you could set some parameters here, like how many bonds could rotate and that sort of things, but a lot of times the default is just as good. And then this software is powerful enough, there's a lot more you could do beyond what I'm talking about, but I'm just gonna give you kind of the bare bone minimum set of instructions. So the next thing you need to do is to set the grid. That's the part of the small protein where you want the ligand to dock to. And the reason why you might want to bias the docking experiment results like that is maybe you already know where the docking or the binding site or the active site of the molecule protein is, or something like that. But even if you don't know where it is, you still have to set the grid. To do so, you need to go to macromolecule to choose the macromolecule. This is the protein that we're docking to. And often it'll ask you to save this protein file, if there's no error found, as a PDBQT file. Okay. That was technically an error, but I think that's going to probably be okay. And then set map type, you want to go to choose ligand, and the PBP is the ligand of choice, so I set that. And the next thing, you want to go to grid box, and the pop-up window should look like this. I don't know if you see the grid box in the middle there. You can move this wherever you want. Okay. If you move this offset gauge, if you want. Okay. But and then if you move this, you can make it bigger. And if you have no idea where on the protein the molecule is supposed to dock, you can make this as big as you want. If it doesn't cover, you can right click here and make the value of the spacing to be a little bigger, like 0.5 or something like that, and then you can cover more territory. But I'm thinking that's probably gonna be enough. I'm just gonna maybe make this 0.4. Okay, that's probably big enough to cover almost the entirety of the protein. This would be called a blind docking experiment, because I don't. I'm just gonna pretend like I have no idea where this should bond or dock, I should say. Once you do that, you want to go to File, Close Saving Current Parameters, and that information needs to be saved as a grid box parameter file or GPF file. So go to Output, Save GPF, and in the same folder you want to save this. Now, I didn't mention this earlier, but you need to, in some versions of the software or in some OS, I noticed that the extension doesn't get saved properly, so you want to add the extension as well. I'm just going to call this the blind gridbox.gpf and save. Now, the next thing you need to do is set the docking parameters. So let's choose the macromolecule. You're going to choose the PDBQT macromolecule file that you saved earlier. And go to ligand, choose, that's going to still be PBP. Where usually the default values here are good. Now, if you want to, you can change the search parameters. Genetic algorithm is sort of the evolutionary artificial intelligence type of algorithm steps that Autodock takes to find the docking information. This top number will decide how many conformations or how many docking poses you want, like top 10 or something like that. We're just gonna do a quick one, so I'm just gonna look for 10 conformations. Often, to get a really precise, well, not really, but pretty good result, you want this to be about 50. And then the population size, you want that to be something like 750 or something like that. But for now, we're just going to do a quick and dirty one. So I'm just going to accept the default value. And once that's all set, you want to go to Output. You could use the Lamarckian algorithm and go ahead and save this docking parameter file or DPF file. So we're just only looking for 10 confirmations DPF. Okay. Don't forget the extension and then save. Now we're ready to run those parameter files, but you first need to run the AutoGrid program to specify grid spaces in which you're going to find the docking poses. Even if these things are pre-populated, you need to still hit browse and then specify where the AutoGrid 4 file that you remember copied from the installed location into the working folder, and then hit open. And if you skip any of this, often it gives an error, and then go to browse and find the gridbox file or GPF file that you created. If that works nicely, it should create the log file name automatically, and then you hit launch. Now at this point, if this window pops up and it immediately disappears, that's likely because there was an error and the AutoGrid program did not run. This should take a minute, even if your computer is really fast. I feel like okay. So AutoGrid, if that finishes, that pop-up window disappears. And once one of the ways you can make sure that that actually worked is if you go to the working folder, you should see a bunch of files that you did not create that ends with .map, like these things. Okay. Now that the grid is set, you can now run Autodock. So once again, you need to specify where the Autodock file is in your working folder and the docking parameter file, DPF file. And if that works out nicely, the log file name should be automatically populated, and you hit launch. And again, if there's an error of some sort, this window will disappear immediately. Again, even if you have a really fast computer, this should take a minute. Now, if an error happens, what should you do? Oftentimes, if you shut everything down and maybe even restart the computer and then try it again, it often works. So try that. But if you saw an error message earlier in the process that we've been describing, you most likely will not see a successful docking experiment. So now, once that finishes, go to Analyze Docking, Open, and then here's a docking log file that's created. And then if you open that, it'll try to open your new ligand that is based on the docking experiment as a separate molecule to be displayed on the side. So that's named PBP2. And then apparently there's 10 docking confirmations found, right? Well, because we specified 10. We'll just hit OK. Just so we're not going to get confused, I'm just going to deselect this so that we're not displaying the original ligand. And it's hard to see this or find this in the cloud of things, so you might want to turn on some other display model, or you could do something like that as well, the spheres to show the molecular surface, but we can kind of see that. Okay, so we're going to go with that. We're going to go back to docking confirmation, play ranked by energy. So apparently here's the best ranking pose. Interestingly, it's very close to the heme, so likely this really would result in an actual reaction between our ligand and the heme. Okay, and then here's the second pose. So put it close, nice. Third is far away enough from heme that might not be realistic. Fourth, fifth, sixth, and the believable result is when you have a bunch of poses that are pretty close together. and like really much lower energy than like other poses. And to see that visually, you could go to clustering, show, to see the clustering of conformations. There's some clustering of this lower energy, binding energy at the beginning. The first and the second poses are clustered together similarly, so that's kind of believable. Now, another way you can analyze the docking poses, if you want, is to go to Analyze Docking and say Show Interactions. So you need to choose the macromolecule first. So the macromolecule we're looking at is that. Specify it, and then go to Show Interactions. It gives you some display options like so. By the way, the scroll thing on your mouse would be zoom in and out, and then right click button moves and whatnot. Anyway, here's the first docking pose with all these interactions. Okay, so and especially if you see a very believable hydrogen bonding type interaction, that's when you know it's probably a believable pose. Let's see if there is such a thing. I actually am not necessarily seeing believable hydrogen bonding type interactions, but oh well. Perhaps some of this kind of makes sense because there's a bunch of aromatic amino acid residues, here's phenylalanine, phenylalanine, that are in striking distance of our aromatic ligand, so perhaps this is believable. If you want, you could save image with a transparent background and stuff like that. Okay, and then you can set where you want to save that and save your image file and whatnot. Okay, so that's kind of how you might use Autodock in a nutshell. I'll kind of give you one more thing to think about, and that is how to save the result. So one way you could do that is select the ligand and select the main protein molecule that is now kind of not visible, so let's display that again. They're yellow highlighted because they were selected. If you select them and then if you click on the current selection and right click on it, you can clone those two things where selected together, and what you could do is select that clone, which is the totality of the ligand and the original protein molecule, and then you can save that as a PDB file. Okay, and once you do, so that's this is a new PDB file I just saved, and once you save that, it's kind of nice because you can open it and manipulate it for further you can manipulate it further in PyMol. So what I'm gonna do is open that in PyMol. So now you could kind of see that it didn't save very well. Oh, it saved the wrong ligand files. I don't know what happened there because that's not reasonable. Those two things can co-occupy the same space, but anyway, I messed up something there, but hopefully you could kind of get the gist of it. And I may or may not make a separate video about PyMol, or you could probably just as easily look up a tutorial video online on PyMol. So hopefully that was useful to you, and let me know if you have questions, and like and subscribe and whatnot.